everyone, I'm Kiara McKenney, and on behalf of the Applied Technology Council, I'd like to welcome you to this webinar on earthquake-resistant design concepts, an introduction to seismic provisions for new buildings. Both this webinar series and the FEMA P-749 guide are divided into two parts. Part A provides an explanation of the basis and intent of U.S. seismic provisions, and Part B provides a walkthrough of the seismic design process for new buildings. So today's webinar is Part A. We hope you'll also tune in next week for Part B. And just to note, you do need to register separately for Part B, so we'll include a link in the chat within the next few minutes if you haven't registered for Part B and are interested. This webinar is brought to you by the Applied Technology Council under a contract with FEMA, the Federal Emergency Management Agency. If you haven't already, you could download the handouts using the link in the chat. If it's not there now, it will show up for you within the next few minutes. We know that many of you are interested in receiving professional development hours for your attendance today. If you are registered and in attendance of the live webinar, a certificate documenting professional development hours will be sent to you by email within 4 weeks. If at any time during the webinar you have questions, please type them into the Q&A window that you can open from the Zoom control panel. We're planning to have a live question and answer session at the end of the webinar, so please submit your questions as you have them rather than waiting until the end to submit them. We'll answer as many questions as we have time to at the end of the webinar, and if there are questions that we aren't able to answer live, we plan to provide written responses for as many as is practically feasible to respond to. I would now like to turn it over to Patia Scott from FEMA's Earthquake and Wind Programs branch, who will provide a brief introduction to today's webinar. Patia, please go ahead.
Thanks, Kiara. Good afternoon. My name is Patia Scott. And as Kiara said, I'm a civil engineer in the Earthquake and Wind Programs branch at FEMA. It's my pleasure to welcome you to today's webinar on Part A of FEMA P-749, Earthquake-Resistant Design Concepts. As part of our responsibilities under the National Earthquake Hazard Reductions Program, FEMA supports activities to reduce future earthquake losses. The primary way we do this is through the development and publication of technical design and construction guidance products, as well as through the support of training and related outreach efforts such as this webinar. FEMA supported and worked with the Applied Technology Council to develop this webinar to provide a tool that communities or other entities could then use to encourage greater protection from earthquake hazards, thereby reducing future earthquake losses. Understanding the basis for the seismic regulations in the nation's building codes and standards is important for design professionals, students, building owners and operators, and many others. So please enjoy Part A of this webinar, and as Kiara said, next week on February 15th is Part B.
Thanks, Patia. So now let me tell you all about your accomplished presenter today. Mike Griffin is president of CCS Group Incorporated in Chesterfield, Missouri. He served on the project review panel for the FEMA P-749 report and was one of the developers of this webinar. Mike has over 35 years of extensive experience in the assessment of earthquake and high wind for structures and non-structural components, equipment, and systems. Mike routinely provides training and education sessions to engineers, management personnel, and students in natural hazards and risk assessments. He holds Master and Bachelor of Science degrees from the University of California at Irvine and is registered as a licensed professional engineer in 8 states. I'd now like to turn the webinar over to Mike. So Mike, please go ahead.
Thank you, Kiara. I'd say good afternoon, which is here, but I understand there's people from around the world that have registered, so welcome. Today, we're going to address Part A of P-749. Get right to it here. P-749 was originally developed back in 2010 to address the same concepts at the time. And so this is a second edition update that is also free, available from FEMA. It's designed it was created and separated this time for the update to address 2 different audiences. One for the general public that want just a basic understanding of the seismic provisions as they relate to our building codes, and then a more deeper dive into it for our design professionals. And so that's Part A and Part B. Today is Part A, where we're going to look at just an overview of earthquakes and their effects on the built environment. The building code development process, that's very key. And then look at what the building code seismic provisions mean in the context of performance. If you design a building to the building code, what type of performance can you expect from that? And that's a philosophical approach that we'll look at. And then we'll kind of wrap it up towards the end and looking at some of the key seismic resistant features that are good to have in our buildings for good earthquake resilient performance. And then look at some common building types and their relative earthquake performance if they're strongly shaken. Part B is next week, as Kira had said, so hopefully you'll register for that. That is a much deeper dive into the actual seismic design provisions and overview. It's tied into ASCE 722 provisions that have just come out, but it's not a replacement for going into 722 directly. But it's a great overview with some references tied back into it. So that's next week if you haven't registered. So before we get started, let's take a quick poll here, and just so we can get an idea where everybody's coming from. So weigh in here shortly when it comes up is select which one most appropriately applies to you. And the first one is you have very little knowledge or experience with building codes. You just want a basic understanding. You're on the end where you say, what's a building code? You really have no experience with it. Second one is you have a basic understanding of seismic design. You know there's provisions in the code and that it's there, but you're not familiar with it. The third one is you're experienced with structural design provisions, but not for seismic design, i.e. you're in a low seismic area and you really don't get into the seismic provisions. And then the last one suggests that you have a high level of experience in both structural as well as seismic design. So take a few seconds, go ahead and weigh in, and we'll kind of see where everybody lands here today.
Great, and it looks like almost 3/4 of people have already responded. So I'm going to go ahead and close the poll in just a couple seconds. And now I'm sharing the results, Mike.
Oh, okay, very good. So majority of you are in the experienced with structural design, but not necessarily seismic, and a little lesser degree with experience with both. So very good. All right, so we've got quite a educated audience. I'll suggest that we have. Okay. So chapter 1 out of part A, looking at earthquake effects. If we look at earthquakes, they occur all the time around the world. If you look at data from the USGS, roughly 20,000 earthquakes occur worldwide every year. These are mostly small, barely feel them unless you're probably sitting on top of them. But then earthquakes being very small, we can also have that large one that can actually do some pretty significant damage and loss of life, as we just saw with Turkey last week. The figure here shows earthquakes from just 1 month, March of 22 of last year. I think most of us from our early educational days understand that the Earth is not solid. We do have a molten core as well as softer areas around it, but we have this very thin overlying crust. And so we look at earthquakes, that it's a function of this makeup of the Earth that causes earthquakes. And it's good to think of this in the context of an egg. An egg has a nice soft core, but it's got a very thin shell on top. So that's very analogous to how the Earth behaves. So we have these plate boundaries, or plate tectonics, which is generally our continents around the world, that are constantly moving due to the rotation of the Earth. And so these plates butt up to each other. And with this rotation, they're trying to move in different directions relative to the adjacent plates. And so if we take two of those continental plates and look at them in terms of their movement, we start from the left and we'll work to the right. Is we've got the two plates, they're joined or adjacent, they're locked together to some degree. Again, this is our thin crust. And they're moving in different directions, differentially from each other. And so they start to displace, slide along each other, try to rotate. And so you're developing this boundary amongst them that hasn't slipped yet, until it becomes so intense that the two plates will then actually slip relative to each other, regaining some of that displacement that they've been trying to impart between each other. And then as a result of that, we get a large release of energy if it's a large earthquake. And then that then is the focus for our earthquake, and it propagates out and radiates away from that area. If we kind of take a look at where earthquakes occur, they occur along these plate boundaries. So the one on the left shows our plate boundaries, our plates as well as our boundaries. And then if we take that same USGS map for earthquakes in March of last year, you can see the predominant location of these earthquakes is along the plate boundaries. If we look at the lower 48 and on the west coast, we can see the Pacific plate boundary there, and we can see a majority of the earthquakes occurring there. We can also have intraplate earthquakes. Look in Oklahoma, for instance. That is primarily subjected to human activity or fracking, is to where we're seeing an increase in earthquakes in those locations. So we can have them generally not as large as we'll see on the plate boundaries, but nevertheless can be quite large. New Madrid there just to the right, southeast Missouri, northeast Arkansas is where we've got New Madrid seismic zone, and that has been historically able to generate very large earthquakes. If we look at some of the effects from earthquakes, we've got kind of a series of effects that we'll walk through here in terms of their general impact to the built environment: fault rupture, ground shaking, landslides, liquefaction, and lateral spreading. We have to keep in mind, though, some of these are very localized effects in terms of our built environment, and others affect a very large geographical area, therefore a very large percentage of our built environment. So if we look at faulting, faulting is generally along our fault traces, our interplate boundaries. And we can have a variety of faults. We can have a fault on the upper left that is a subduction zone, to where we've got the two plates. One's trying to dive under the other, and the other one's going up, riding up over the top. So we get some vertical displacement in there. The middle one is we've got lateral displacement, where the two plate boundaries are trying to slide across each other. And we've got a condition to where they could actually be pulling apart from each other, depending on the movement between the two different plates. We can have a combination of those as well. So if we look at a couple examples here on the left, we can see we've got a horizontal or lateral offset of the faults by the fence that's been displaced. On the right, we've got a vertical offset that has occurred. It's good to know where these faults are, particularly if they rise to the surface, because we don't want to build a building across the top of a fault. Will not survive. California has done a very good job because they've mapped the known faults in California. The Alquist-Priello study has mapped these faults or zones. This is showing the Hayward Fault, delineated by a boundary or a yellow zone on either side of it. And so California has restrictions on what can be built within these zones today. Now, there are buildings that are on it because they were built prior to developing these maps. But nevertheless, current design and construction for buildings across these zones have to meet certain requirements before it'll be allowed in California. These are actually can be mapped. You can plug in your address and see if you're in California in one of these zones, which is kind of fun to do. Ground shaking. Now, ground shaking is our most damaging effect as a result of an earthquake. Number one, it causes the greatest damage. It also affects a very large geographical area from the ground shaking. And some of the other hazards we'll look at are more localized effects, like faulting is localized. So ground shaking, think of it as ripples in a pond. You drop a rock in a very calm pond, and what happens is you generate waves. At the very beginning, they have a fairly high amplitude, and then as they radiate out away from that center, they die out, the amplitude dies out or attenuates until it's completely gone. Well, the energy from the earthquake focus does the same thing. Once the earthquake occurs, it radiates out away from that, and it dies out or attenuates as it gets further away. So if you can imagine, similar buildings, if they're closer in, are going to sustain much higher degree of damage than buildings that are much further away, that shows in the pictorial here. Another condition that we need to keep in mind for ground shaking as it's exposed to our buildings is what type of soils are our buildings founded on. This can have a pretty significant impact on the degree of shaking applied to our foundation systems and therefore our buildings. If we have buildings that are supported on very competent soil materials like rock or dense soil, that energy radiating from the earthquake will have little amplification as a result of traveling through those types of soils. However, if we've got less competent soils, think of soils along riverine valleys. They're loose, unconsolidated soils. The energy from an earthquake, due to its dynamic characteristics, can actually amplify as it transmitted through those soil layers. That translates to our building foundations in our buildings and shakes our buildings much stronger. So having a good understanding of what the soils are underneath our buildings is very important to obtaining the actual motion we have to design the building for. And the building seismic design provisions take that into account. Some of the measurements of earthquake severity are earthquake magnitude, Richter magnitude, intensity, and then also what we need as engineers. So let's look at a few of those. So here's Richter magnitude. It's a logarithmic scale. So every point increase, 5 to 6, is a 32-fold increase in the amount of energy released from the earthquake. Now, this is great for understanding how large the earthquake is, how much energy is being released, but it doesn't tell us anything about the degree of damage. For instance, if we had a large magnitude 8.0 earthquake out in the middle of the ocean, shaking-wise, is that going to affect us here in the continental 48? Well, no, it's not. We're not going to feel it. So location is also a big parameter that needs to be taken into account. So just Richter magnitude doesn't mean much to us. We need to know the close or proximity of it is to our built environment in terms of its impact. To give us a little bit of an understanding of this log relationship between the increase in magnitudes, this is kind of a creative slide that was created of various earthquakes that have occurred over time of different relative magnitudes increasing to show by the diameter of the circles the difference in amount of energy released of the various earthquakes. So we're going to start here very, very small and then work up to the largest earthquake that we know about. amazing. Another descriptor for amount of energy released is modified Mercalli intensity scale. This is much more informational to us in terms of the extent of damage as a result of an earthquake that has occurred. And so it's a scale of 1 to 12. And what it is it's a qualitative based scale. This takes into account damage at the current site of which it was measured at. And that's informative because it also takes into consideration amplification from soils. And so if any of you have gone to the USGS website, earthquake hazards, and logged into the You Felt It section, because you've just felt an earthquake, they will ask you a series of questions of what you felt from that earthquake shaking where you are at. And so you put your location in, and then it'll ask you the questions. And what it's doing is mapping what you felt in terms of damage or felt conditions into one of the 12 MMI scales. And then they map all of that. And so it's emergency managers use MMI as well, but this is not very useful for us as engineers for building design. What's more useful to us is the actual dynamic characteristics for the earthquake shaking. And each earthquake is different in terms of its response and dynamic characteristics. And so what's much more useful is the displacement, velocity, and accelerations for the earthquake mapped over time. And so these, then we can develop an actual spectral response for the earthquake, for this particular earthquake. We can then apply that to our models for our buildings, and we can actually design our buildings to resist that level of earthquake or a family of earthquakes that have differing dynamic or characteristics, frequency characteristics for our buildings is how we typically do it. So this is much more informative for us in terms of design relative to Richter magnitude and MMI. Landslides, this is a localized effect. And so you can imagine if we've got slopes that are steep, formed of poor soils, we can actually engage these and then cause failures. The one on the left is from the 1994 Northridge earthquake in Southern California. And the one in the center is Government Hill in Alaska during 1964 in Anchorage. Liquefaction. This is a localized effect based on soils. We need three things for liquefaction. This is like quicksand, to put it very simply. We need to have a loose granular sediment soils, poor soils, water content to water table has to be high, and then we have to shake hard. So we have a lot of buildings right down today that are located on poor soils, have a high water table, and they're doing just fine. Well, we haven't shaken them yet. So that's the third ingredient. And this little video here illustrates what happens under poor soils, high water table, and you shake hard in terms of building stability and what it does to our foundations. So the shaking increases water pore pressures, and then this liquefies the soils, creating the quicksand type condition. And then we lose our soil bearing strength to support our built environment, our buildings. And then we have settlement of our buildings. This is an example taken from a building during the 1906 San Francisco earthquake. So it's kind of a layer of loose granular sediment. Here's our high water table. A load's being applied just from the soil weight in our buildings. Now we're shaking it. Pore pressures are increasing. We can get these sand blows as it injects out because we're increasing the pore pressure that's underneath our built environment. We can get settlement and then therefore building damage. Here's a good example of soil liquefaction where we've got a sewer system that actually was buried with just sand over the top rather than gravel materials, and it actually lifted out due to the high water table and the shaking. We can have lateral spreading, again, another localized effect due to the soils and the degree of shaking. How do we use this information in terms of our structural seismic design? Geologists and seismologists look at known seismic activity on faults, where the faults are located, what's their likelihood of producing earthquakes of differing magnitudes, what's the highest magnitude, as well as much more frequent lower magnitude events. It looks at the intensity of that type of shaking. That impacts the geographical region that might be impacted. And so all of these parameters are combined to generate, perform a seismic hazard analysis to generate shaking levels, of which we use in the seismic design provisions. The three most common seismic hazard maps that are generated as a result of this seismic hazard analysis is really the 475, 975, and the 2475. These are return periods associated with the probability of ground shaking exceeding what the seismic hazard analysis at these return periods show. And so these are incorporated into our building code structural seismic design provisions. This map here is showing shaking intensity as a result of the maximum considered earthquake that's used in the building code, which is roughly a 1,000-year event, return period event. And you can see from the white colored areas, that's minimal or low level of shaking. And then as we proceed to the darker colors is where we have the higher degree of shaking, therefore higher degree of damage associated with it from the potential. You can see it's not just a West Coast problem. We've got areas outside of the West Coast that exhibit high levels of shaking where seismic design should be performed to make sure our built environment performs well. So we've got a hotspot around the New Madrid seismic zone, as well as around Charleston. If you'd like more information on earthquakes and their effects or impacts, a good reference is USGS or FEMA websites, a lot of material there, as well as the P-530 document, Earthquake Safety at Home. Appendix A within P-530 has a nice summary of each of the major earthquake regions around the country for the US, if you want additional information. Remember, anything that says FEMA in front of it, in terms of these guides and reports, are free. You can download them from the FEMA website. It's a fantastic resource. I always look at it, well, it's our tax dollars at work, so take advantage of it. All right, Chapter 2. How are the seismic provisions developed and implemented? Well, let's kind of walk through a typical process for a building. Generally, what happens is you've got a developer, owner team that envisions a project, what they want to do. They secure funding for it, and then those aspects are all worked out, and then they start to engage the design professionals, and that's architect generally leads that, and then they hire the structural engineer, the civil engineer, mechanical, electrical, fire protection, etc., to be part of that team to develop the developer owner's vision for that particular building. Once those design documents are developed, then contractors take over and they actually then build the building to what the design states. And there's the construction managers, general contractors, GCs, and subcontractors that are involved in that aspect of it. We also have regulatory conditions for most parts of construction, represented by building officials and various inspectors that perform inspections during construction to make sure that the construction is in compliance with the design. In addition to that, there's also special inspectors and testing agencies for certain aspects of the building construction based on the materials used, where we want to verify that we've got proper strength in accordance with the actual design. Understanding the building codes, these are a local item that are adopted and enforced by state and local governments. It's not on the federal level. We have to understand that it's for the protection of life safety and the welfare of the public. Furthermore, the building code seismic design provisions represent a minimum set of standards and requirements for life safety. And it also provides a level of, so developers can't cut corners, and therefore safety, it provides a minimum level of performance that they have to achieve through the building codes. Most of the local building codes use a model building code with amendments or modifications to suit their particular needs, environment, etc. And most of those are based on the IBC, or International Building Code, created by the International Code Council. The US is unique in that our building codes, as well as our consensus standards, we'll talk about here shortly, are developed by private organizations. They're not developed by the federal government, as other countries around the world are. And this applies to the technical provisions as well. So it's a little bit of a unique perspective in terms of how our building codes are created, updated, and evolved. So here are some examples of building codes where municipalities have taken upon themselves to modify a model code to suit their particular needs and then call it their own. So you've got the California Building Code, City of Los Angeles, New York, you've got Seattle, Chicago, again, based on the model code, but modified for their unique characteristics. And you can imagine City of Los Angeles, New York, Chicago, Seattle, they've got tall buildings versus a very rural community in terms of what they might be putting in there for some of the enhancements over the model building code. One key thing to remember, though, about our building codes is that they are not enforced consistently across the country. And since they are adopted and enforced at the local level, you can imagine, based on the community resources, that's going to vary. So if you've got a smaller community that's adopted the building code and they're enforcing it, but they really don't have a building official to actually implement plan checks and construction inspections over a large city that does have a building department to do that, you can imagine that the enforcement of those codes are going to be quite varied. And in fact, that's what we see pretty much outside of the West Coast, is enforcing the seismic design provisions is hit or miss outside of the West Coast. And so we could have quite a few buildings that are still being built without proper seismic design attention, as they should have been if the code was appropriately applied. So if we look at the consensus standards based on our materials, concrete, masonry, steel, and wood, these are developed similarly by design professionals sitting on members of these associations that sit on these committees and develop these documents. In the early days, these guidance documents were put right into the building code verbatim. Today now, they've been so standardized through ANSI standards that the standards are now referenced directly from the model code or the IBC directly, rather than putting them directly in there. So instead of one document that we have to utilize for structural design, we've got the building code, and then we've got all the standards along with it. And here's some of the standards. We've got ASC 722 on the left. We've got the concrete or ACI for concrete construction, design and construction. We've got masonry, we've got wood, and then we've got steel on the far right, in terms of our consensus standards that are referenced from the building code today. We also got to remember that our codes are not just for structural seismic. They cover a variety of elements for safe life safety construction for our built environment. So structural stability, fire resistance, egress, ventilation, all our plumbing, mechanical systems, energy efficiency within our buildings are improved as we adopt and enforce the current code. And so all of these things are enforced by the local jurisdiction. And so you can imagine they've got their areas of expertise. Oftentimes it's not seismic in terms of the enforcement. They'd rather look at these other elements first versus seismic. So that's where we get this kind of differing enforcement for structural seismic provisions around the country. Codes, they're adopted locally. They become law. They're enforced by the entity, and that might be a chief building official, might be the fire marshal, might be a clerk. Those entities are known as the authority having jurisdiction. So AHJ is often referred to it. And when we have that, that's law. So it's illegal to construct a building unless the AHJ issues a building permit. They will then normally do a design plan review to ensure conformance to the building code design provisions. And once they approve that, then they'll issue a building permit and construction can begin. And again, this varies based on jurisdictions. For example, in Missouri, where I'm from, the state does not have an adopted building code. Larger cities like St. Louis and St. Louis County have adopted building codes. But if you're out in rural Missouri, there legally is no code that has been adopted by the local jurisdiction, county or city or municipality, that you have to adhere to. Now, what we'll generally find is that our design professionals doing designs will adhere to the latest in that case, but not always. So it varies across the country. So here we have the HJ that has issued a construction permit. There's a series of inspections that go on as a result of the construction that's there. That's spelled out in Chapter 17 of the IBC. So we're establishing conformance to our design. Once all of the inspections have been performed satisfactorily to the AHJ, they will issue an occupancy permit and the building can be occupied and utilized. After that becomes an existing building, and then the AHJ can actually revoke that occupancy permit if if you have damage associated with fire, earthquake, or tornado that may create unsafe conditions, they can revoke that occupancy permit until adequate repairs have been made in that regard. What about existing buildings? As soon as a building gets constructed and occupied, it becomes an existing building. Within the ICC, they have the International Existing Building Code, which addresses this. So most buildings, if nothing is done to them, they essentially don't have to bring their buildings up to code every 3 years when the new code comes out. They're subject to the code that they will at original design and construction. However, within the IEBC, there are triggers that may require a building owner to bring the building up to current code that's in effect at the time. And that is due to additions, occupancy changes offers one of those triggers, substantial alteration or repairs, damage from natural hazard to fires or other incidents that may require upgrades, alterations, or repairs that then would trigger whether or not an owner has to bring the entire building up to current code. What about all these existing buildings that we're worried about their seismic safety? Well, it's not generally cost effective to upgrade existing building structures to conform to present new code provisions. Just totally different in terms of the requirements enforced at the time to current code provisions. So there's compromises, and there's a standard that addresses that, and that's ASC 4117 for seismic rehabilitation of existing buildings. That's based on prior FEMA documents. We'll talk briefly about here shortly. The IEBC references ASC 4117 in terms of the requirements from that necessary when you trigger one of these upgrades for existing buildings. Some jurisdictions may adopt ordinances separate from the IEBC or IBC that require mitigation of some of the risks to more vulnerable building types that they might have in their inventory. Some of these examples where you'll find these mandatory or adopted ordinances is on the West Coast, is for unreinforced masonry buildings, CMUs, RMU. These are very vulnerable buildings when shaken. And so many of the West Coast have URM ordinances to actually mitigate some of the risk associated with those. Non-ductile concrete buildings, so older concrete frame buildings is another one. Tilt-up buildings, pre-Northridge steel moment frames, so pre-1994 moment frame connections. If you're in a high seismic shaking environment today, under the current building code, there is only a handful of seismic moment frame connections that a structural engineer can use. Wood frame buildings with soft stories. That's a particularly vulnerable one that could cause loss of life. And so some municipalities have ordinances to address those conditions within their jurisdiction. An owner can do a voluntary upgrade if they so desire. And so there's quite a few. This varies very significantly if you can think about it. They can range from doing just minor, maybe non-structural component improvements within a building to major structural retrofits or strengthening for the building itself. These could be done all at once, one-time deal, or an owner might look at doing this incrementally throughout the life of the building, a short life, 5-10 years type of program. There's good resources associated with doing an incremental seismic retrofit. They're more cost effective to do it that way. And the FEMA has some very good documents that are very specific to certain industries, hospital, commercial buildings, schools, to where these programs are kind of delineated, and very good guides are provided in these FEMA 390 through 400 and 420 documents associated with that. And then if you're looking at non-structural components, which can be a source of life safety risk, E74 is probably the go-to document for both a layman understanding for non-structural component earthquake risk, as well as design professionals and what to do about it in terms of mitigation. Another good tool or reference is FEMA 547 for existing buildings and structures. This is somewhat of a companion document on implementation of ASC 4117 for the evaluation of existing buildings. So we mentioned that our building codes, as well as our consensus standards, are developed by individual private organizations and not the federal government. Does the federal government do anything? Sure they do. The U.S. Constitution reserves the right to the states for anything that the federal government doesn't regulate. And therefore, building codes is one of those. It's not in the Constitution. And so that's all delegated down to the local state or municipalities. That's why we also tend to see this differing adoption and enforcement of the seismic provisions, because it's on a local level. But the U.S. government has provided a significant amount of assistance and incentive to perform earthquake mitigation and proper seismic design through the development of the National Earthquake Hazards Reduction Program, or NEHRP. And under NEHRP, there are several organizations that support research, better ways to design and construct our building structures for seismic. Again, this is earthquake. Development of design documents and guidance for developers to improve building codes. There's seismic hazard maps developed through the USGS in terms of updating the seismic hazard maps, which get updated about every 6 to 8 years. And there's also hazard mitigation grants that the federal government municipalities can apply for these grants for increased seismic resistance for their built environment. And as Patia mentioned earlier, this class is one of the other ways that the federal encourages mitigation through training and education. So NEHRP, again, there's these 4 entities. FEMA's kind of at the top. We've got NIST in terms of doing research and development of increased technologies that then find their way back up into the building code if they become beneficial. National Science Foundation for funding aspects, and USGS for looking at the seismic hazard that are incorporated into the building code. If you're interested in more information on any of these are good resources to go to obtain more information. So if we look at chapter 3 and keep in context what the purpose of our building code is, we can begin to look at what the design philosophy for seismic safety is within the building code. So this is right out of the IBC 2021 1.01.3. Emphasis added, it's to establish minimum requirements, reasonable level of safety, health, and general welfare through structural stability, strength, means of egress. And so in here, you won't see anything that says earthquakes. It says protection from hazards of fire, explosion, or dangerous conditions. You can imply earthquakes, high wind, tornado, that sort of thing, but doesn't specifically say it. It's a set of minimum requirements. For seismic safety provisions within the code, those provisions are balancing life safety versus the cost of design and construction, with the fact that we are larger earthquakes, which are infrequent. What is the probability of that level of shaking being experienced by our buildings over its normal lifespan of roughly 50 years? So we're balancing these three things in terms of the seismic design provisions. So if you design to the building code seismic provisions, minimum set of requirements, you are not getting what many people refer to as an earthquake-proof building. I've heard that so many times, it's amazing. You're not getting that. There is a level of damage that is expected if a building is subjected to a very large level of shaking. How it does that is, for the acceptable risk, is primarily based on occupancy and function of the building in a very somewhat prescriptive manner in terms of the seismic provisions. So for more normal buildings, ordinary buildings, risk category 1 and 2, which are roughly 90% of our built environment, falls into these two categories, or really two. One is agricultural buildings, so they're not heavily populated, if at all. Category 2 is our normal buildings, office buildings, that sort of thing. So that's 90% of our building environment. So again, protection of life safety, accept damage as long as it doesn't threaten life safety. And we really look at that in terms of a very low risk of collapse in any earthquake. So in that high level of earthquake, we don't want a building collapse because that affects life safety. Important structures, risk category 3, that's for higher occupancy structures, schools, large auditoriums, to where we have a higher degree of safety we need to maintain. So our buildings are designed to a higher level of performance. And then we have a last category, risk category 4, is our essential buildings. And those are hospitals, police, fire, EOCs, to where we need good performance out of these buildings because we need them to function fairly quickly, if not right away after an earthquake. And so that they're designed for that. But that's a very small subset of our Hurricane Katrina, 2004. If we look at functional or recovery from major natural disasters, 80% of pre-Katrina levels, New Orleans has only achieved to this day. So a lot of people left and they didn't come back. Christchurch, they lost a majority of buildings in their central business district that they had to be demolished because damage was too severe. Then we've got the Mayfield, Kentucky tornado outbreak that nearly flattened an entire city as it went through. So communities are much slower to recover if they have a severe natural hazard impact their community. So this idea of the seismic provisions being based on acceptable risk is being rethought. And we'll speak to that here in a minute. But we do know that if we have increased performance for our built environment, that's less damage. That should be lower insured losses, lower rates, as well as a significantly reduced recovery time and cost associated with it. So better performance equals that. Future directions with regard to this that are being considered and actually evaluated is, should we be looking at this more from a functional recovery approach versus a more prescriptive, accept some damage, but life safety is our goal. So it's facility dependent. So critical facilities and infrastructure become more important. So we design to a higher level of attention, acknowledges some damage, but that has to be acceptable. And then it also looks more importantly at what type of recovery timeline do you want for your particular building? Is 2 months okay? Is a year okay? Looking at it from that perspective. Some of the challenges associated with this different philosophy is identifying building occupancies and infrastructure. What constitutes important or critical? What about the design criteria associated with each of these differing categories? What do we do about the existing building stock that we have out today? That's important because that's most of our built environment right now. Do we improve our design and repair standards for lifeline infrastructure so we get a better functional level of performance out of them during a natural hazard event? And do we look more appropriately for lifelines in terms of redundancy and resiliency? That often isn't looked at to a great degree today. So these are being considered. There's another alternate approach for seismic design, and that is performance-based design. That's addressed in the text of P-749, and that's P-58. And the P-58 guidance documents can be obtained from FEMA or ATC, and they have been used for structural design, seismic design for buildings. Right now, they've been used, aware of, primarily for high-rise or tall buildings. Have been used very effectively in that context. That's a different approach from the building code provisions right now. More information on these alternate methods or philosophy for earthquake design and recovery is contained in the FEMA P-2990 document. And so you can reference it here and then download that. Okay, so the last two sections, let's kind of go through some of the key elements for what we need to achieve good earthquake performance in our built environment. So if we look at structurally our buildings, and what do we mean by that? Well, that's our foundations, our columns, beams, our floor plates, our roofs. That's what we mean by structural elements. That's what the structural engineer designs for seismic safety as well as the other building modes. So important characteristics that we need to look at. We want stable foundations. We want continuous load paths, adequate stiffness and strength. We want regularity within our buildings. We want redundancy as well, ductility and toughness, ruggedness, and then adequate separation or adjacency from adjacent structures. So let's look at each of these. So foundations, we need to be stable in terms of transmitting the building's loads to our foundations, to the soils, and that includes gravity as well as lateral loads. So our foundations have to be able to transfer the forces generated within our building structures to the soils via the foundations. We have to account for large horizontal forces from a wind or earthquake, and where our foundations and our structural systems have to respond to that. We can accept so much deflection. If we have too much deflection, we can actually start to incur what we call P delta effect, or gravity becomes an overturning or failure mechanisms for our building structures. So we have to accept only a certain amount of deflection within our buildings, else will become unstable and then will collapse. So if we look at stable foundations, we have liquefaction that we looked at earlier. So we want to make sure that we understand what the soils are. If we do have liquefaction, can we mitigate the effects of liquefaction to a degree? Because we know we're going to get some level of settlement and rotation within our buildings. How we do that is via shallow foundations or deep foundations in terms of dealing with those soil inadequacies or vulnerabilities. Spread footings are our most common type of foundation system that we have today. And that's where we've got just a spread footing, strip wall around the building, or supporting just individual columns that are supporting both our lateral and our vertical loads for the building. If we know we've got poor soil conditions underneath, we might consider a raft foundation, again, a shallow foundation where we put the entire structural system on top of this mat. It's very large, deep, stiff. And so that can accommodate differential settlement within our soils for the whole building, acting as one. If we can't achieve our objectives for stable foundations with shallow, then we have to go deep. Here's an example of a deep foundation. We've got a mat type system for our structure, and we've got piles that go down to more competent soils beneath the structure, or possibly even down to bedrock that are resisting our forces. Another very critical aspect to seismic design is what we call our continuous load path. This is vitally important. If you think of an anchor and a chain on a ship, if you break one link, what happens to our anchor? It sinks. So we've lost whatever load resistance holding the ship back that we have with the loss of just one link. We'd like to have a continuous load path. We actually like to have a redundant load path in case one does break. We've got an alternate path to actually resist our loads. If you look at our buildings at rest, no problem. But when we excite our buildings with lateral loads, seismic, we shake the building back and forth, and we have a continuous load path, each of the elements are connected appropriately, we can actually then begin to look at resisting that motion from the earthquake. If we don't have a continuous load path, i.e. our connectivity between our structural elements are compromised, then we can begin to introduce an unstable condition within our buildings, and then we have collapse, which is very life-threatening when we have collapse. So here's an example of a continuous load path condition where we failed the edge of the roof anchored to a ledger to the house structure here that failed, and then we induced collapse. Here's an example of precast panel with our roof diaphragm where those connections separated and the panel basically out of plane response pulled away from it and collapsed, causing, again, it was also supporting the gravity loads for the roof, caused the roof to experience a localized collapse at those connection failures. Here's a good example for wood frame homes that are on a cripple wall system. So there's a crawl space underneath to where we failed the cripple wall. The home has displaced laterally and failed that. And also we have lack of anchorage between the sill plate of the home and the top of the foundation system on the one on the right. Here's several examples of a continuous load path, critical elements there that if we shake them, that we can create unstable conditions and cause partial collapse. This was taken out of the P-530 document, and so there's more examples in there if you're interested in looking at that. We also need for our buildings to have adequate strength and stiffness. So our buildings have to be strong enough to resist the lateral forces generated, inertia forces generated from the earthquakes, the large earthquakes. And we also have to have stiffness within our structures. So just having the strength is not enough. We have to have the ability to not displace significantly to where we can overturn our structure. So we have to have stiffness to actually keep that within check. We also want regularity in our buildings, structures. So this has more to do with how our loads are transferred or continuous load path through the structure into where if they get down to the base of the structure where our forces are the highest, that if we could have a discontinuity in our construction that introduce a vulnerability to where we might introduce building collapse. So if you look at the building on the left, we've got a condition to where we're very regular above, and then we get down to the first floor foundation, or the top of the first floor, and you see we've got a series of large openings versus what's above that. Well, that's introducing a stiffness within our building structure that's less than what we have above, and our forces are higher, so we could be introducing a collapse mechanism with this type of irregularity at the base of the structure. Similarly, we see in a lot of buildings where the first floor has tall columns, and then the floors above are much shorter and regular. That introduces a potential irregularity or soft story in our building structure that could precipitate collapse. So as structural engineers, we have to watch for that and design for that to account for those conditions. Soft story or weak story irregularity. Here's a great example. In this, many of the West Coast municipalities have mandatory ordinances to retrofit this particular type of vulnerability. So this is a wood frame apartment building that sits on what we call tuck under garages. In the plane of the garages, in and out, we've got separation walls that go all the way down the structure. So earthquake forces in that direction have a path or load path to go down through those shear walls down to the foundation system. But if we look the other direction across or parallel to the garage door openings, all we have is the short piers between the garage doors. And garage doors are not shear walls. And so what we've created is a very large, massive structure above with very little lateral support or system at the base of the structure to resist the lateral forces. And what it ends up doing is it precipitates collapse. So this was in the 1989 Loma Prieta earthquake in the Mission District. Quite a few failures of buildings were sustained because of the soft story failures. We can also create a condition within our buildings to where our lateral systems in each of the directions are not similar, to where one direction allows our buildings to displace more than the other direction. And so we can then begin to look at introducing torsion within our building response, and that actually can cause pretty significant damage and collapse of our buildings in very little time. As soon as you get a building rotating, it starts to really tear itself apart pretty quickly. A very common irregularity that we have to look at for design is what we call reentrant corners. Nature loves symmetry. Give me a rectangle or a square and throw an earthquake at it, and it just does great, both directions. But now you start adding wings off of buildings, and you now have structural extensions of the building that are dynamically behaving differently than the adjoining section. And so where these wings come together, we have the reentrant corner, and that's where we have very high stress concentration areas. So the transfer of seismic forces between those two has to be designed very carefully so we don't introduce a potential damage mechanism. That's our reentrant corner. We love to see redundancy in seismic design. We don't like to rely on one element to actually resist all of our seismic loads. We want to be able to transfer to other elements in case we have a failure of one for whatever reason. And so often, if you look at wood frame construction, which is highly redundant, studs 16 on center, our trusses are 24 on center, we have a high degree of redundancy to where if we fail a column, a 16 stud, 16-inch on center stud, pull that out, what happens to our load? It just redistributes to the adjoining studs, and then we're okay, we're fine. Think of it as suspenders. If our suspenders are great in terms of holding pants up, but we lose those and we have a belt that's left. And a belt will do not as adequate a job, but it will do the job. Here's another example as to where we've got a condition where the upper structure shows one large shear wall that we've been designed for resisting seismic forces versus the lower one that has individual larger piers that each have been designed to take a portion of the seismic load. And so if we have a failure of the single shear wall up above, we have no recourse in terms of retransmitting the seismic force, lateral force, along the rest of the structure. Whereas at the base, or the base structure, the bottom structure, we have that capability to transfer into the other elements. Sure, we'll get more damage, but we've got additional capacity as a result of designing with redundancy in mind. We also need our structures to be have ductility and toughness within them. Ductility is the ability of our structures to undergo significant lateral displacement without collapse. That's the intent behind our life safety provisions. And so we don't design for the full maximum earthquake that could occur in any particular region of the country. We design for something much less. And to go along with this acceptable risk, that's why. But we also require for these high seismic shaking environments that our building maintain a level of ductility that's required by code, that in case that maximum earthquake did occur, that the maximum, the building would undergo displacement, but has ductility to avoid collapse. That's how it's handled. Again, that's acceptable risk. So ductility is very, very important. Where we see problems is our older buildings don't have ductility built into them. And so they become particularly older concrete frame structures, URM masonry structures, they become very vulnerable to collapse if shaken strongly. So here's a unreinforced masonry building. We've got some localized collapse to our exterior walls. And so it's good strength up to a point, but then if you push it too hard, you're going to crack that wall. It's going to break up. We have no ductility left after that. How do we achieve that? For brittle materials like masonry or concrete, we put reinforced steel appropriately designed and detailed in that to achieve that additional ductility and toughness within our buildings. This is a good example of concrete ductile frame construction versus non-ductile, so older concrete frame buildings. Generally, these are multi-story. So here's an individual column from our concrete frame buildings, and we're going to cycle this back and forth due to seismic shaking, and we'll see the difference in performance as we go through there. This was pulled out of an article that a columnist in the LA Times wrote. He handles earthquake issues. He does a great job, and it's quite illustrative of ductility. So here we go. So we're cycling back and forth. So which building would you prefer to be in? Oops, back, sorry. So in our non-ductile condition, in concrete frame buildings, our concrete takes our vertical gravity forces, whereas our steel takes our lateral forces in the building. And so in our non-ductile condition, we're breaking up all of that concrete and causing it to just fall out. Well, we don't have any vertical support anymore. The steel cannot take vertical loads that were there for the concrete to take. That's the difference between the two materials. And so that's why these become collapse hazards and are very important to either retrofit or get out of our built environment. Adjacency, so we do worry about adjacency for structures. We don't want to build a new structure next to an old one because both buildings will move in earthquakes, and so they can actually pound and cause damage. Non-structural components, another potential life safety risk. Non-structural components are everything but the building structure. So there's a lot of things that go into this. They're categorized by architectural elements, MEP or mechanical, electrical, plumbing, and then really a category that includes everything else, which is really the function of the building. So it's furniture, fixtures, equipment, contents, manufacturing equipment, that all falls into this category. The code addresses it to some degree, but not in a very robust manner. Again, it looks at it from a life safety perspective, not post-earthquake functionality. Here's some examples of architectural elements. That's our ceilings, our partition walls, our exterior cladding, glazing, chimney, stairs. Elevators actually come under the architect, under architectural components. They're responsible for this design as well as seismic. Our MEP systems within our building to provide our comfortable environment that we work in or live in. So that's could be pumps and chillers, our air handlers, distribution panels, all of our ductwork and conduit, as well as our HVAC systems. And then FF&E. So this is everything else. File cabinets, partition walls, cubicles, computers, TVs, chemicals, whatever's in the building. It generally falls into FF&E. Here's an example of a soffit that was shaken in the 94 Northridge earthquake that fell down. So if you were trying to vacate the building during the shaking, this likely would have fallen down on top of you. That's why we need to stay in place until the shaking is stopped. Here's some interior partition walls. Notice the ceiling is completely gone, lost all the pads, and we've got some localized collapse. Non-structural components, particularly the architectural elements and our piping and conduit systems and duct systems, they're attached to our building structure in multiple locations. So they're very sensitive to how the building moves. And so that displacement, building displacement, has to be accounted for when we're looking at these types of components in terms of good earthquake response. Here's showing some cladding or glazing that's in the exterior wall. That has to accommodate our building movement, else it's going to break and fall out. If you want more information on non-structural components, here's some great guidance documents, E74 being one of the best. And then there's these individual ones for mitigation. If I have to mitigate an HVAC duct, what do I do? Well, I'll just pull up the P-412 and look at it because it has conceptual retrofit diagrams in there for how to do a brace for a HVAC duct. They're great tools. They're almost pocket size. And then E74, which is one of the best ones. Oops. I just messed up. Hang on. There we go. All right, chapter 5, our last one. Let's look at some of the structure types that perform and how they perform in earthquakes. The building code recognizes these types of systems in terms of structural seismic design. And if we look at bearing wall systems, one of our most common, we've got the bearing walls that are taking both vertical and lateral loads through the structure. And then we see it typically for light frame construction, low-rise commercial and warehouses. Here's examples of our wood frame homes in terms of residential bearing wall, as well as commercial apartment buildings. Here's some commercial warehouse type facilities, as well as then office buildings, bearing wall systems. Again, they take both vertical and lateral loads. Performance, generally, if you can get the loads into the bearing walls, the lateral loads, they perform very well, even if marginally reinforced. For our older buildings, we'll develop these X cracking patterns within the shear wall segments between the windows, down low, where our portions are higher. If we have a tilt-up structure, we might lose an exterior wall if our connections aren't appropriately designed and detailed. We can have building frame systems. This is where we've got two separate structural systems. We've got a frame system that is taking all of the gravity loads for the building. And then as soon as we excite the building laterally, for seismic or wind, any other lateral load, we've got a separate structural system that is actually just those forces. And so that could be a brace frame, that could be shear wall, that's providing our lateral resistance for our building. Here's an example of the building frame system and where the architect has let the structural engineer kind of expose their lateral bracing system. This is somewhat unique, and most of the time the architects like to hide these lateral systems or braces within the structure. And we can have moment frame structures. And so these are reliant on the connectivity or stiffness between our beam column joints in certain areas of the building structure. So these, as you can imagine, are very flexible buildings. They're much more flexible than a shear wall building or a brace frame building. But they do provide a lot more open space within the structure. And so a good example is here. And if you look to the right on the high-rise section, you'll see the joints between the beams and columns are quite different from if you look off to the left in the lower rise section. That is indicative of a moment frame style connection. Pre-engineered buildings, these are steel framed, they're lightweight, they're single story, there's not much weight on them other than some lights and maybe some fire protection up on top. And they actually perform very well in earthquakes. We can have dual systems to where we've got moment frames and shear walls or brace frames. Where we typically see this type of construction is to where we're sharing lateral loads between the systems. The shear walls or brace frames provide our lateral stiffness predominantly, and then our frames are designed to take a portion of that in terms of the lateral loads. These are generally used for tall building design, and stiffer systems, the shear walls or brace frame, reduce our lateral drift, and it's much more cost effective in terms of design and construction. Cantilever columns, these are generally pretty poor performing building structure types, particularly in higher and stronger shaking. And so the code limits where you can use this type of system depending on the type of shaking environment that your building structure is in. So lateral force resisting systems, the code prescribes 3 different types associated with our different building types, or whether it's a frame, a bearing wall system, a moment frame, etc. We can have an ordinary system for seismic response. We really aren't doing anything special other than normal structural design in that context. This is generally for low and moderately low seismic regions where this is allowed. You are designing for a higher seismic force in your building as a result of this, but there's no special detail. Then we have a next step is intermediate, which is used for certain lateral systems. It's not as good as special, which we'll talk about here shortly, but it does require a higher level, or does require a level of connection, particularly detailing, than ordinary. Then we have special, which is our highest performing systems. And so there's a lot of special requirements in terms of structural design and detailing associated with this, because you're relying on additional ductility within the building system. And therefore, there's going to be a lot more inspections in terms of what needs to be inspected and checked as a result of construction to make sure that we have that level of detailing to provide the level of performance that has been designed. The code also goes into non-building structures, and some of those are tanks, water towers, chimneys. Not everything's included, but the code does address that in Chapter 15 of 722. Example of non-building structures is structures you see at a refinery. So let's look at a quick summary. Key elements for good building seismic safety is our hazard and soil conditions, understanding those. Important code adoption and enforcement within our jurisdictions will yield much better performance. We have to understand what the building code seismic design today gives us, and that's an acceptable risk approach. Doesn't mean earthquake proof. Some of the key elements for good seismic performance is having a good continuous load path, building configurations, no irregularities. We have good ductile detailing, and we address non-structural components because those affect life safety. And then understanding our basic building types relative to good earthquake performance is important for structural design. So let's take a quick poll question here and look at first one. It says, let's select which is the most important element in achieving good seismic performance for building structures. First, application and enforcement of the building code requirements for building structural seismic design, designing a continuous load path, performing seismic design for non-structural components, or all of the above. Just take a couple seconds to weigh in. We'll see where everybody lands.
Great. The answers are pouring in. About half of people have answered. So just a few more moments before I close out the poll. All right, Mike, I'm going to go ahead and close it.
Okay. The majority, 87%, said all of the above. That's right. I mean, we need a building code that's enforced. We need our continuous load path. We do need to address unstructural components for good seismic safety in our built environment. So very good. I guess I did well then. All right.
You did a great job, Mike.
With that, I'm going to turn it over to Kiara in the question and answer session.
Great. So before we dive into questions, it looks like we'll have probably 7 or so minutes to get through some questions that we've received. But first, I'm going to go through some housekeeping items. If you are looking for a PDH certificate, you'll receive one automatically, assuming you're here live. It will be sent to your email within 4 weeks. Due to the large volume of participants, please be understanding that we cannot make exceptions to our PDH policy. If you have any questions that you haven't submitted, please go ahead and type them into the chat. We will get through as many as we can before our time is up, and then Mike will respond to many or all of the questions you receive after the webinar. So you'll receive a spreadsheet with the responses to questions we don't get to. And then lastly, if you enjoyed today's webinar and are interested in learning about the seismic design process for new buildings, we encourage you to tune in next week, same time, same place, for part B of the webinar series, which will be presented by Ron Hamburger. The registration link will be placed in the chat within the next few minutes, and you can also find it in the email publicizing this webinar. So
next week with Ron on part B will be very good, but expect to be very technical as well.
And this, I think, Mike, this is part A is a really, really great base for part B, I would say. So if you are interested in the subject matter of part B, I think this part A will have prepared you really well. So with that, I see questions coming in. I've been reviewing questions as they've come in while Mike was speaking, and I've highlighted a few in particular to go over. If we don't get to your question, it doesn't mean it wasn't a good question. I think I tried to pick out questions that were more general in nature and of interest to potentially a larger group of people. So if we don't get to you today, hopefully we'll be able to provide a written response to you after the webinar. So Mike, are you ready?
Yeah. Okay.
So I think a really common question that's been coming in is related to current events. So I don't know if how closely you've been reading about the Turkey earthquakes, but a lot of people are interested in hearing your comments about why those events were so devastating. And I'm hoping that you could set it in the context of the many themes we've been talking about today with seismic provisions.
Sure. Understanding I haven't dove deep into looking at what's happened over there. I've just read several articles. I understand what the magnitude is. I understand from some of the pictures what the building type looks like to me. So in that minimal context, I can offer my observations. A 7.8 is a large earthquake, and so you are going to get some really high levels of shaking. I'm not familiar with the soil conditions over there, but there could have been some poor soils where we had some additional amplification of that energy from the earthquake. So that being said, what I've seen in terms of some of these low-rise apartment structures is that they appear to be concrete frame with what we call masonry infill walls, just to kind of close it off. They tend to be that type of construction in this area tends to be non-ductile. And so likely what happened is, from what I've seen, is that you've got this type of construction with the first floor around the base not having as much in terms of infill walls, i.e. storefronts and whatnot, that have created a soft story, and that has precipitated collapse. And so it also looks like it might have also been somewhat of a domino effect. One structure collapsed, hit the next one, that precipitated additional collapse, because you can see kind of a sequential event for multiple structures that are adjacent to each other. So quite a few things that go on from what I've seen just initially. very, 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 very devastating. I have gone around the world looking at earthquake damage, and my worst earthquake was in 1988 in the Armenia earthquake, where 25,000 people died as a result of building collapses, thousands of building collapses. And that's a life safety issue. We can have damage, we can have a lot of damage, but collapse, you are likely looking at loss of life. And that's very, very problematic for older structures, particularly.
Thanks, Mike. And a lot of the themes come back to overall earthquake resistant design concepts that this report is really about communicating in an approachable manner.
Right, and implementing.
Mm-hmm. So we'll give you a question about the New Madrid area, seeing as you're located in Missouri. So someone wrote, it seems that there are no tectonic plates in this area. So what is the cause of the New Madrid earthquakes? So, and maybe you can explain again a little bit about what the New Madrid region is.
The New Madrid is what we call an intraplate. So we've got the Pacific plate and the Atlantic plate, and New Madrid sits pretty much right in the middle. And so as our continental plate starts to rotate, we're generating these interior forces as well. This is my understanding. I'm not a seismologist or geologist. So we're developing these internal forces pretty much in the center of the continental plate. And that's introducing additional stress there. We also have the Mississippi embayment. That is a big bowl from the rest of the continent in terms of structure. And so I believe that contributes to why we have earthquakes here. They're not frequent like California. I mean, in terms of large or moderate or large quakes. But in 1811, 1812, they had a series of 3 magnitude 7.8 to over 8 earthquakes, plus just thousands of moderate and smaller level events back then. And so we generally, well, although we saw that in Turkey, they had 2 very large events go one day and then the next for another one. We don't design for multiple events in an earthquake. We design for one event. So we're relying on this ductility and the acceptance of damage. But now you have a damaged building and now you get hit again with equal or larger earthquake. What's going to happen to our built environment? You have a damaged building. The odds are it's not going to do as well. So it's kind of an interesting conundrum in terms of how do we address that. We can't design buildings for no damage. That's going to be much, much too costly. So when we look at it from acceptable risk, it's an interesting challenge in terms of how we technically address that. But for New Madrid, there's site of the largest earthquakes recorded in the continental U.S. in New Madrid, not California.
Great, thanks, Mike. So we're technically out of time. I'm going to try to squeeze in one more. So you use the term critical lifelines. So can you explain what you mean? What are critical lifelines? And there's also a question about if utilities such as gas lines can be constructed across a fault.
Water, power, you got sewer, right? It's really all of our lifelines that promote life for us to live. Water being a big one in terms of that regard. So you've got the water treatment plants, you've got the water sources, you've got sewer treatment. There you've got power. Is it electric? Is it gas? Can these infrastructure lines be cross faults and sustain no damage? Yeah, there are techniques that are being used that can be used when these are constructed to actually avoid differential displacement and therefore impact to these systems. If you look at Alaska in terms of the oil pipeline up there, they're crossing all these tundra zones that are moving all the time, and they've created expansion joints that are accommodating these types of displacements. So yes, you can. I mean, think of riverine crossings. It's the same concept in terms of trying to deal with these types of crossings where you've got essentially a void, you got to resupport and then accommodate any differential movement. So yeah, definitely you can.
Great, thanks, Mike. So I think we're all out of time for today. I'd like to give you a big thank you for your presentation today. I think it was excellent. And if those of you in the audience are interested in more, please tune in next week for part B. Just a couple other quick notes. There is a survey link that will pop up when you leave. We really appreciate if you take a few moments to fill that out, especially to provide inputs on topics you'd like to see covered in future FEMA webinars. We definitely look through that information really closely to select future webinar topics. And then many of you have asked about recordings. There will be a link to a recording provided in an email within the next day. You'll also receive the link to the handouts again and a link to the survey. So, and Mike, any parting words?
We've got quite a large group that for structural engineers. I encourage you to sit in on Ron's presentation next week. You won't be disappointed.
Agreed. So with that, I think on behalf of FEMA and the Applied Technology Council, I'd like to give thanks one more time to Mike for his presentation. I'd like to thank all of you out in the audience for joining us today. And this concludes the webinar. Thank you.
Bye.